discussion section, um, so people can watch it later. There are people that are enrolled in the discussion that are in like Hawaii, France, Arizona, everywhere. So I'll just record and leave these online so you guys can watch it whenever you want, or if other people cannot watch it live, you guys can come back and watch it. Um, I will have, if you guys, I think you guys can see the like Renan's iPad in there. Um, I'll use this iPad to share my whiteboard. Um, I hope you all can see the whiteboard. So we can like go over the homework by writing on it. I think it's an easy way to share whatever I'm writing and thinking. So today I'll go over the homework one, just quickly pass through it and see if you guys have any questions. So this is the homework. I'm sharing my screen. I don't know if you all saw it, but it's on CCLE, so you can download it there. Let's see the waiting room. Can I admit it all? There are people trying to join. Yes. Okay. I think everyone or most of people are in. So I have the homework is on CCLE. It's due on Tuesday at 11:59 p.m. So make sure to turn it in before that so you can receive the full credit for being on time. If you cannot for any reason, like something happened, just make sure to email us, either Sanjay or any of the TAs explaining your reason, so we know that you're dealing with any problem that you might have. I know that everyone is kind of all over the place right now, but we're all together, so don't think in case you have any problems, just email us. So the homework, what happened here? Okay. So the homework has 5 questions or 4 questions. The fifth, yeah, 5 questions. The last questions from a book, and the other 4 questions, I think Sanjay created it, and I'll go over every single one with you guys, just explaining basic things so you guys have a general idea of what you do. So for question number 1, it's about total maximum daily load. So imagine that a river, any waste generated by an industry, they kind of treat the waste a little bit and then they dispose in the river. But there are regulations that that you need to achieve in order to dispose your waste. So for an example, if you're disposing chloride, you can just dispose it in a certain amount per day, depending on the river, depending on the region you are, depending on the laws that are applied for your area. And that's because the river has a capacity of treatment. So if you put too much contaminant, the river is not going to be able to treat all of that naturally. And then it's going to be toxic for the organisms or fish and people downstream using that water for irrigation. They're going to be using your contaminant along with it. So every river has its own law. And the EPA keeps checking, it creates the law for every river or every stream or every water body. And it checks, I would say like weekly, like what are the concentrations of the contaminants in the river. And they create these reports that they leave it online. So you can access these reports and check the concentration of the contaminant, if it's above the limits, if it's below the limit, as well as the report that they created for every contaminant regarding how much the river can receive of that contaminant. and everything is online in this website here. So let me share this screen here. So if you click on that website, this is the website that it's going to open, or if you click on that link, and you can look at any report that is available throughout the US. If you know the name of the stream, or if you know the general area that you're interested in. So for our homework, we are interested in the Ballona Creek, which is a creek located in LA. Usually, I think it passed through Culver City and goes all the way to the ocean around Marina del Rey. So if you type this in here and you search, this is a very kind of like complex website. There's a lot of information, so it's normal to be overwhelmed because there's a lot of links, a lot of back and forth that you can click. But basically, you put the name of the creek, the water body that you are interested in, and these reports are available here, or the water results. And for Ballona Creek, there are many different ones, right? There's the Ballona Creek wetlands, there's the Ballona estuary, there's the Ballona Creek. In our case, we're interested in the Ballona Creek, but but they are like all related to each other. So if I type in on Google Ballona Creek, let me just show you guys how it works, so you guys have a general idea of how to approach this question. So UCLA, there's someone coming in. Okay. So UCLA is over here in Westwood area. This creek, the Ballona Creek, it comes in this direction here and goes all the way to the ocean. So if we zoom in, you can see the creek here. It's a very, if we see this picture, it's not that big of a river. It's just, I don't know if you can see it, but it's a very low stream. You can literally cross the creek by walking on it. So this creek, the water, it gathers all these stormwater from LA because, you know, LA is highly dense and there's a lot of impervious pavement. So all this water that comes in, it ends up going to this creek or to other creeks around. And there's a lot of pollutants. So this creek goes to the ocean, but before it enters the ocean, it enters this Ballona freshwater marsh here, which is called the Ballona wetlands. And that's where most of the contaminants are actually removed. So if we go back to the EPA website, you see that there are water results for the Ballona Creek, for the Ballona wetland, which is that wetland before the water goes into the ocean, and so on. So you can see that you can access any reports that you might be interested in. So in our case, it's the Ballona Creek. So if you click on it, oops. This is the page that it opens, 2016 water body report for Ballona Creek. And so the causes of impairments for reporting year 2016, these are all the TMDL reports that they created, meaning that for every contaminant, so let's say copper, the Ballona Creek has its own capacity to treat a certain amount of copper, right? So they create this report looking at copper, looking at the copper's toxicity, looking how much rainfall we have, how big the river is, and then they create this report saying, okay, this creek has a capacity to treat this amount of copper, and they detail all the study in this report. And they did that for copper, for indicator bacteria, lead, trash, and so on. There's one here that's cyanide that it's still needed to be completed. So that report, it's still being built based on this table. So if you keep moving down, here it shows that in a certain week they took samples and they analyzed the concentration of indicator bacteria and in the river, and they saw that the concentration was above the limit. So that caused a problem for the river, cause of impairment, because the concentration is below the limit. So they need to make some actions to reduce that contaminant in the river. And if you see here, indicator bacteria and all these other contaminants, they found to be above the limit at some point in the year of 2016. So then they know the TMDL, right? They know how much of that contaminant is can be in the river, and they know that the concentration was above the limit. So they need to create some actions to address those problems, and those actions are um, um, discussed in these reports here. So if you see this table, you can click on this report and this report is about cadmium and how they address the cadmium problem that they had in the river. So if we open this, and then we click on, put in here, wait, where is, here, TMDL report. So this is the whole report that they have, meaning they have the limits for every contaminant that they are like, oh, this is how much this river can receive. And then they have, oh, in this day, this is how much it received and was above the limit. And then because it was above the limit, these are the actions that we took to reduce the concentration of the contaminant. So these documents, 71 pages long. I don't recommend reading it all. But if you want to skim through it, it's very straightforward, other than these law regulations here that I don't understand. When it comes to water, it's pretty straightforward, and it's usually shown as tables. So if we go here to loading capacity, they say the TMDLs are developed for cadmium, copper, lead, silver, zinc, within the sediments of Ballona Creek estuary. So you see that although we are in, I think the estuary and the Ballona Creek, they're pretty much the same. They have the same TMDLs. So based on the rainfall and how big the river is and so on, they calculated that the loading capacity that the river can receive is 8.5 kilograms per year of cadmium, 241 kilograms per year of copper, and so on. So these are the limits for the creek. And there are many other information in this report that you can find. And yeah, that's pretty much where you address. Oh, someone's saying something here. I didn't see. How do they set the limit? So someone asked David, how do they set the limit? Is it based off what the water is being used for? So they set the limit based on the toxicity of the contaminant, right? If it's too toxic, they're gonna be like, hey, you can barely put any of these contaminant here. Um, and then how much rainfall you have every year. If you have just a little bit of rainfall, you're probably not gonna be able to put any contaminants inside the river because you barely have any water flowing in there. But the ultimate goal to set all this up is for the water is being used for what? First, is the water being used for irrigation, or is the water being used for recreational activities like people swimming in the river or lake? And yeah, I would say that those are the main goals, or also to preserve the ecosystem of the river. You don't want to kill any living organisms, any microbiome that the river might have. So the ultimate goal is to preserve the river and offer good water quality if people need it for either recreational activities or using for irrigation or using in your house. So yeah, that's the main reason. All right, so let's go back to the homework. So yeah, based on this website here, you can answer all these question one here. It's a lot of information in the website, so feel free if you cannot find something or if you are confused, you can email me or Anesh or Sanjay asking for any clarification. But if you read, it's very straightforward, most of the parts. Let me see if someone said something on chat. Sorry, I'm still getting used to this whole system here. All right, couldn't find the TMDL limit for the wetlands, Maggie said. The TMDL, let's see if I can share the, so the TMDL limits for the contaminants, based on this report that I opened here, these are the contaminants that they are reported. And this is the TMDL limits. So for copper, the TMDL is 241.6 kilograms per year. For silver, it's 7.1. So, and if we go back here, and remember, you don't need to report for question one, you don't need to report every single one in every single document. We, like Sanjay and Anesh and I, we want to make sure that you guys know what TMDL means and knows how to find one TMDL in a document. Because in the future, you're going to be working for a company and the company produces, I don't know, silver, and they dispose silver and they need to meet the regulation, and they're going to come to you guys as engineers and be like, hey, how much of this silver can we put into the river? So you need to have the general idea of where to find this piece of information. So no need to go through every single document in this page and find every single TMDL. We just want to make sure that you guys know how to approach and find this information, because as an environmental engineer or environmental science major, it's important to know where that information can be found. But yeah, it's inside these documents here. You can find the TMDL. All right. So let's go back to the homework. So Maggie, I hope I answered your question, but if you have any other questions, feel free to email me if you're still confused of how to find the TMDL. But it's basically those numbers that I just said. So question two, now we're gonna get into writing or like solving problems. So I'm not gonna, of course, solve all the problems, but I do want to give you guys a general idea. I'm trying to share the screen. You cannot start screen sharing while the other participants sharing. Oh, okay. Let me share the content here, my board. All right, so I hope you guys have, I cannot share two things at once, apparently. So I hope you all have the PDF for the homework one open so you can follow what I'm talking about. So I'll discuss now about question two. And it's a very straightforward question. There's not much going on. It's more about this total maximum daily load and how to calculate and understand the overall process. So question two, let me start. All right. So Q2A, let me make sure that this is being shared. Yeah. All right. So for Q2, it says that you have this stream, this river flowing, and it receives waste from this road. It's like a road runoff through a pipe. So what I like to do in every single problem like this is to draw the overall picture, because it makes me understand the problem better and faster. So imagine that this is the stream, right? Then you have water flowing in this direction with a flow rate of 10. And then you have a pipe coming in from a property. What's happening here? Right. From a property, and it has a, oops. Sure. It has a flow rate of 5. Sorry for my writing, but it's really hard to write in a in a iPad, and I've never done it before. So and then the stream's chloride concentration upstream of the pipe. So right before the pipe, the concentration is 12. So here the concentration is 12. You know, the water is flowing this direction, so the water is going to end up here to the right. And the runoff pipe discharge has a chloride concentration of 40. So the pipe here, the concentration equals to 40. And chloride is a conservative substance, meaning that it's not going to decay, it's not going to be removed by anything. So any mass, the main kind of understanding that you need to have of this problem is that any mass that goes into the system is going to come out. So I'm putting, the pipe is discharging 40 whatever chloride inside, and the stream already has 12, and this whole mass is going to come down. So question A, it asks for, write the mass balance equation for the chloride, and so for effluent chloride concentration, what is the downstream chloride concentration? So you know that, oh gosh, kind of created a thing here, which is not working very well. So we know that Q here is going to be, you know, the Q that's coming in, which is the flow. So whatever water comes in needs to go out. So it's going to be, you know, the water from the pipe plus the water from the river. And then the concentration here is what we want to calculate. So the concentration, based on the mass balance, you can find this concentration downstream. And Sanjay already actually gave you guys the answer, but we want to make sure that you know how to calculate. So the reason why Sanjay gives the answer is because he wants you to know that you're doing the right thing, basically, you know, because it doesn't matter if you do the wrong thing and then you don't, not just you don't receive the full credit, but like you don't really understood the problem. So it's important to know what's the right answer and be able to find it. So based on this picture that I just shared here, that's how you can try to, oops. Okay. So I hope you guys can see this properly. Oh, okay. Sorry, this one's not being shared. Oh, sorry, Maggie. I just saw your question. So it's the same for the creek and the wetlands. Oh, so back at the TMDL. So imagine that the creek is much smaller than the wetland. So because it's a smaller system, you cannot really treat the same amount of contaminants. So I would say, in my perspective, if you have a really big river, it's probably going to be able to treat more contaminants than a really small river, right? Imagine of an industry that produces, I don't know, soda. a big industry can process more things than a small industry. So it's the same concept. The bigger the water body, the more it can kind of, you know, treat the contaminant and reduce that contaminant to a less toxic contaminant. So yeah, perfect. All right, so back to question 2. So 2A, you can, oh, here's, all right, so 2A is to write down the mass balance. So whatever it goes in here needs to come out. And then what is the downstream chloride concentration? So based on this mass balance, you can find the C out here at the end. Okay. So question B now, so Sanjay started like tweaking all the different parameters that you have in this. So you have many flow rates coming in, or 2 flow rates coming in, 2 concentrations coming in, and 1 flow rate and 1 concentration coming out here at the end. So for question B, it says, assuming pipe flow to be constant. So this is 5 here. So this stays constant. And then what is the maximum daily mass of chloride that can be discharged through the road runoff pipe without exceeding the water quality standard of 20 milligrams per liter? So now what do we have? We want to know what's the concentration in the pipe here. If the concentration here needs to be 20, because that's the maximum concentration that you can have in the river. So you're going to solve the problem in the same way as we did for question A, mass balance, and figure it out how much, or calculate this C here. And once you know the C, he's asking, what is the maximum daily mass of chloride? So it's basically the TMDL, right? So TMDL, it's gonna be Q times C, right? Because Q is, let's say, liters per day, and C is, let's say, kilograms per day. Sorry, kilograms per liter. So when you multiply these two, you get rid of liters. So then you have kilograms per day, which is how much, what is your daily load, which is the TMDL. And this C is gonna come from this calculation up here that you're gonna do in question B. Okay. So then C, question 2, part C, it says, assuming the concentration of chloride in pipe discharge to be constant, 40 milligrams per liter. So now I'm just erase all of this because we're changing a different parameter now. So it's saying that the concentration in the pipe is constant now. So this is 40. And then it says, what is the TMDL that can be discharged through the road runoff pipe without exceeding the water quality standard of 20? So now you have 40 milligrams coming. You still have the 20 downstream because that's the limit. And you want to know the Q of the pipe, which is the X. And you know that the Q out is going to be X plus 10, right? So again, you have one equation, which is the mass balance equation, and you have just one variable, which is X. So you're going to solve this for X, and then calculate the TMDL at the end again. which is Q times C in the pipe, where this Q here, it's going to be the X that you calculated up here, right? So this is part C. And then part D is to compare the TMDL of, it's written wrong. It's not A and B, it's B and C. So you need to compare the TMDL of B and C and see which one's greater is Y and explain conceptually. So whenever you're explaining, think of why one is why the TMDLs are different. What is happening, like in the physics behind it, based on how much contaminant you're putting in and how much water you're putting in, and try to think like, oh, this is more diluted than the other, or like this is more concentrated than the other. You know, try to understand why, because the TMDLs are going to be different. So try to understand. There is not, I wouldn't say there is a right or wrong question for this. It's more so you can think and like develop your thought of how and why it's different. So yeah, any questions about Q2? All right. So Q3. Let me open a new whiteboard here. So this is, oops, I'm writing. So Q3, it talks about a lagoon. So imagine like a lake that receives water, you know, and probably this lake is used, imagine if you're from California, you probably know Lake Tahoe. Imagine like a lake like that. It's a big lake where people use for recreational activities. And you kind of need, you know, you need to know how much contaminants coming in. And if that contaminant, for some reason, the concentration of that contaminant coming in changes, you need to know what is going to happen to your system, how long it's going to take for your system to, you know, be in a bad water quality, so then you can close the recreation activities for that part. So those are the implications that happened if you solve this problem. So Q3 here, oops, let's again draw the overall picture. So we know what we're doing. So there is this lake that has a volume, it's a steady flow, and it receives 100 cubic meter per day for a long enough time to assume that steady state condition applied. So that's right. So you have a river here, or a lake, sorry, that receives this stream. And of course, this is not going to accumulate inside the system. So it's going to come out, you know. So this is in, this is out. And because it's a lake and the lake is always there, you can assume that the Q in equals to the Q out. I'll try to use this again. So, oops. It's not working. All right. So you know that Q in and Q out, they're the same. And I'll call this Q. Okay. So now they say the waste entering the lagoon has a concentration of 10 milligrams per liter. So this, the concentration here equals to 10. Assuming complex mixed conditions. This means that the concentration coming in is the same concentration for the whole lake. So what would be the concentration of pollutant? So part A, what would be the concentration of pollutant in the effluent leaving the lagoon. So there are two things happening here. There's a stream coming inside the river or the lake, and then there's stream coming out. But there's one other way that water can come out, which is through evaporation. But because Sanjay didn't say anything about this, you can say, or you can assume that the evaporation is zero. Usually the evaporation is zero. So whatever is coming in, it's going out. You have constant contaminant coming in and contaminant coming out. So what is the concentration of pollutant in the effluent leaving the lagoon? So, it's very straightforward. You don't have anything else varying. So the concentration, it's the same concentration in the lake, which is the only source of concentration coming in. So that's very straightforward. And then for B is if the input waste concentration suddenly increases to 100 milligrams, what would be the concentration in the effluent 7 days later? So now it's where things start getting a little bit tricky, but it's not that hard. I'll just show you guys a graph so you can have a better idea. You need to use a non-steady state equation here that I think Sanjay went through in class. So one thing to think is that, imagine that do I have a marker here? Oh, yes, I do. All right, so imagine that the concentration of the contaminant, or the contaminants coming in here, right? So, and it takes a certain time for this contaminant to pass through the river and come out, right? And this time depends on first the flow rate that it's coming in. So if the flow rate's super fast, of course the contaminant's gonna pass really fast, right? But it also depends on the volume of the lake, because if the lake is, let's say it's like a really small lake in the middle of UCLA, there's not much space for a lake there, but a very small lake, sorry. So the contaminant, it's not gonna take much time to pass through the lake, right? Because it's a small one. But if it's a really big lake, like Lake Tahoe, it's gonna take a really long time for the contaminant to move from point A all the way to point B because it's a big lake. So to calculate this time, we know that flow rate, oops. So we know that flow rate equals to the volume divided by time, right? Because it's always these two dimensions. It's how much water you put in a certain period of time. That's the flow rate of your pipe or of your river. So if we rearrange this, we know that time equals to the volume divided by Q. And you have the volume of the lake that it's given, I think 1200. And you have the flow rate, which is 100. So you know the time in days that it takes for the contaminant to move. Let's say that this is in and out. So you know that what is the time for the contaminant to move from this point in all the way to the point out, based on this equation that it's given down here. So you can calculate this time of the contaminant to go from the inlet all the way to the outlet. And this is gonna give you an approximation of what is gonna happen in 7 days. So if we, let me create a new word here. If we draw a graph, let's draw a graph of concentration out by time. So at the very beginning of the problem, we knew that the concentration in was 10 milligrams per liter. So nothing else was happening to the contaminant. The concentration out would be the same. So if we draw this graph, we start with the concentration of contaminant right here, right? This is the concentration out. It's the same because it's steady. Then the concentration in the inlet start increasing from 10 to 100. What is going to happen at the same time at the concentration at the outlet? Nothing's going to happen, right? Because it's far apart. So if you increase the concentration here, it's not that it's going to suddenly increase the concentration in the outlet. It's going to take a time for this contaminant to pass through the lake. So although you're already receiving more contaminant, your concentration in the outlet is still steady. But after a little bit, this concentration starts increasing. It increases, and then it finds a new steady state, which is the CN, right? That makes sense. So the overall question here is, what is the concentration out after 7 days? So is 7 days here, or is 7 days here, right? So you need to, using the steady state, the non-steady state equation, you're gonna find what is this concentration, or what is this, based on time 7, is this the concentration, or is this the concentration, or is this the concentration? We don't know. So this is the overall idea of looking at the problem and thinking, okay, now I understand what is going on here. I know where the contaminant is coming from and where it's going to. So this is what you're gonna solve. And have this graph in mind, because it's easier to visualize what is happening whenever you have a picture, at least in my case. So someone asked, I'm wondering what is the time when calculating the concentration in the effluent at Q3 part A. I wonder what is the time when calculating. So for part A, let me go back here. So for part A, you don't really need, if you do the mass balance here, if you do the mass balance here, and you know that Q in equals to Q out, you don't really need the time there, right? Time is not a variable because the concentration is not varying with time. So you don't really need the time there. You have Q in equals to Q out. So whatever mass is coming in, it's or whatever mass is going out. If you have just one source of concentration in, that should be the same concentration going out, right? Because the mass that comes in equals to the mass that goes out. Okay, so time is not a variable because concentration is not varying with time at part A.
Sorry to interrupt you.
Sorry, say that again. I couldn't hear you. I think the internet's not very. Do you want to type in? Maybe it's better. Let's see if she's gonna type in, or he. I don't know. So yeah, basically in. So then why in part B we're giving a specific time? So in part B, we say that the concentration in the influent increased for 100 milligrams per liter, right? As you said, it's going to take time for all the pollutants to move to the effluent. Exactly. So for part B, let me move here. So based on this graph for part B, you have the concentration coming in. Let me draw this. So you have the lake here, and you have your contaminant coming in. This is your contaminant passing through. And you have 10 milligrams per liter at first. So if we give a specific time. So part A, you don't need a time because the concentration is not varying. In part B, the concentration is varying, so you need a time. So part A, because you have the same concentration all the time and it's not varying, you know that whatever is coming in is going out. There is no, time is not a variable there, okay? But part B, the concentration is varying, which increases from 10 to 100. So imagine that your contaminant is here and it's passing through the lake and coming out. And it takes a certain time for the contaminant to pass through. So if you increase the concentration in, these contaminants still gonna take a time to pass by and increase the concentration in the outlet, okay? So imagine, let me draw the lake again here. So again, you have the lake, you have the contaminant coming in, and then it takes, let's say, like 10 days. I'm just saying that. Take 10 days for the contaminant to go from the inlet here to the outlet here, out. Okay, let's say that it takes 10 days. So if you take a sample in the outlet at day 2, if it takes 10 days for the contaminant to get to the outlet, if you take a sample at day 2, you're not going to find that contaminant there, because the concentration is still increasing. Everything's being mixed in here inside the lake. So for part B, because your concentration is varying from 10 to 100 in the inlet, every day in your outlet, you're going to have a different concentration coming out. Okay. And that, to calculate that concentration, you need to solve the non-steady, or solve this problem for a non-steady state using a non-steady state equation. Because your concentration in the effluent, in the influent, is going to increase suddenly from 10 to 100. And in the effluent, it's going to increase not suddenly, but gradually, as I showed in this graph up here. Let me draw it again. So concentration, concentration in the effluent, this C out coming, and it's steady, and then it starts increasing, increase until it finds a new steady state. Okay, so she said, okay, thank you. So in part A, everything is steady state. So my mass balance, we're able to know C out. Time only matters in non-steady state condition, right? Right. Well, it also matters in steady state depending on what you're doing. But yeah, in this case, you can assume time doesn't matter for steady state, and then time matters for non-steady state. But in this specific question here, Q3, always reanalyze if you're applying. Don't apply the same concept to other questions, because I don't know if that will be true. But for this question, you can say time, it's not a variable for a steady state. Yes, because your concentration is coming in. You're welcome. All right, so we just have 10 minutes left, and I'll go through Q4, and then Q5 is pretty much the same from the other ones. If you know how to do Q4, you're going to be able to do Q5 as well. So for Q5, or Q4, sorry, let me open a new whiteboard here. So Q4 says, a lake with constant volume is fed by pollution-free stream with flow rate of 50. So again, let's draw the lake here. You have a stream coming in. The volume of the river is given, 10 to the 7. And you have the volume coming in, which is 50. And then it says a factory dumps this waste, 5 cubic meters per second of waste with a concentration of 100. So let's say that the factory is here, coming in, and then the Q from the factory is 5, and the concentration is 100. Okay. The pollutant has a reaction rate coefficient. I'm gonna open this one here because it's easier. Sorry, I'm just opening a new PDF. All right, so the pollutant has a reaction rate coefficient K of 0.25 per day. So we know that this pollutant has this decay rate of 0.25. That means that like every day, the pollutant is reduced by a factor of 0.25, if that makes sense. So if today you have 1, tomorrow you're gonna have maybe like 0.8, depends on the equation that you're using. So the day after tomorrow, you're gonna have 0.6 and so on. So it's gonna be decreasing with time. But you also need to take into consideration if you're putting more contaminant in. So everything's gonna be together. All right, so you have this K, and then the problem states, assuming the pollutant is well mixed in the lake, find the steady state concentration of pollutant in the lake. So we have 2 streams coming in, have the stream of the river that has, it says pollution free. So the concentration here is 0. And then you have this factory dumping waste inside at a flow rate of 5 and 100 milligrams per liter, I guess. Yes, of concentration, and you have this K of the rate of the river or the factory. So everything's gonna come into the lake, and there is an effluent, right? There is a water coming out, which is gonna be a Q, and it says that the volume of the lake is constant. So the Q coming out needs to be the 2 Qs coming in, 50 and 5. So that's how you can calculate the Q out. And then it's asking, what is this concentration out here? Okay. So by using this steady state equation, you do a mass balance in this problem. Whatever is going into the system is equals to whatever is coming out. And you're going to have a reaction there, right? The reaction is consuming your contaminant by a rate of 0.25 per day. So you know that the Q in from the stream, the pollution-free stream, it's not going to contribute for any contaminant there, right? And that's a really important thing because of this C, the C0 here. This is not really going to affect anything because the volume doesn't change and it's not adding any contaminant. So all you need is here and here. Okay. Well, this Q here, it's gonna depend on this Q and this Q, right? The 50 and the 5. So you actually need this part. But for the concentration of the contaminant, the string coming in is not gonna really affect anything. Okay. And then you have the rate here of how your contaminant decays. So you know that whatever comes in minus the reaction, right, which is your contaminant decaying, needs to be equal to what is coming out, right? Because you're putting, imagine that you're putting a bunch of things inside of a river or a lake, and then things, and then I'll get to this question, but imagine that you have um, a glass of water and you put things in, and you know, then you drink that water. Everything you put in, you're putting, it's coming out of the cup, right? But now in this case, now you are putting things in, and for some reason they're being consumed. So it's not that everything's going to come out. So part of it's going to come out, and that's going to depend on this K, um, um, the reaction rate here. Okay, but if you, it's a very straightforward problem. So if you use the equation, the steady state equation, you can solve it, because you have, all you need to calculate is this Q here. You know the Q out, you just need to calculate the C out. All right, someone asked, sorry to interrupt you, but for this problem, are we going to find C in the lake or C in the effluent, or they are the same value in this problem? So you're calculating C out, but because you're we're saying that it's a steady state, we the C out is basically going to be the same C of the lake. Okay, because we're assuming that, you know, the lake has such a big volume that if you put a little bit of contaminant in, which is so the lake has 10 to the power of 7 cubic meters, and every second it receives 5 cubic meters. So 5 cubic meters near 10 to the power 7, it's so little that the concentration in the lake is all the same. It's all mixed well. So the concentration in the lake is going to be the same concentration coming out of the lake. And you want to know the concentration coming out of the lake. So you can calculate, because if you're trying to calculate the concentration inside the lake, you are not really closing all the borders about the mass balance, because you're saying whatever goes in stays in, and that's not true. Whatever goes in is also coming out. But you, in the general picture of the problem, the concentration in the lake equals to the concentration in the effluent. So yeah, it's a very straightforward problem. It's one equation, and you have all the data or all the variables other than C out. So you can calculate that C out. And I don't think Sanjay gave the answer for this one. But in case you have any problems, you guys can always email me. I'm not gonna have time to go through Q5. Sorry about that. But based on what we discussed before, it's the same concept. You have, it's pretty much the same from Q4 actually. So you can apply the same, yeah, it's steady state as well. So you can apply the same overall thought to solve the problem. So yeah, feel free to email me. Do you guys have any last minute questions? We have 1 minute. I can stay for longer if you need as well, but it mentions figure 7. Does it matter that we don't have figure 7? Oh, you guys don't have figure 7? I can, let me see here. I think figure 7 would be, I have the figure 7 here because of the book. I'll share the figure 7 through email. Let me just write this down, just in case you want to have it. But it's basically, you know, these, let me open. It's basically like, you know, this lake that I drew here. These, it's basically an equation. It's an exemplification of whatever is coming into the lake is going out, and all these variables. So you don't really need the figure 7, but I can, I just took note of this, and I'll share the figure 7 with you guys, just so you have it. But yeah, in case you guys have any other questions, feel free to email me. We can always set up a Zoom meeting to solve any questions if needed. I have my office hours on Wednesday, but the homework's due on Tuesday. But in case, again, if you have any questions, email me. I can answer through email, or we can set up a meeting if it's necessary. Any other questions? All right. So thank you for joining. I'll see you guys next week. And again, just email me if you have any other questions. Could you also resend the Zoom link for office hours? Yes, it's in the email that I sent, but I will, I send the email for discussion section. Just below it, there is a office hour, but I'll send it next week. I'll send the office hours again so everyone has it. Perfect. All right, just email me if you guys have any other questions. And yeah, stay safe, everyone. Bye.